Hello, my name is Keegan Goodell, and this is my lab experiment video for Lab 2, where we analyze the magnetic field of a bar magnet. The purpose of this experiment was to find the distance dependence of the magnetic field created by a bar magnet, to computationally model and calculate the magnetic field produced by a permanent dipole, and to compare the theoretical and experimental distance dependence measurements. The main concepts of this experiment include magnetic fields and electric currents, the Biot-Savart law, sorry if I mispronounced that, which the equation for the magnetic field produced from a dipole is derived from, and they are also included on the slides. Distance dependence, which shows that the strength of the magnetic force between magnets decreases as the distance between them increases. The magnetic field produced far from the bar magnet is equivalent to the magnetic field produced by a permanent dipole. And as you can see, there is a quick preview of the results of the experiment down in the corner. As for a quick run through the procedure, using a magnetometer sensor on a phone, align the magnetometer chip with the magnet to ensure proper reading, which we use tape to mark on the phone. Make sure the initial BX component is 0. For the parallel magnetic field calculations, calculate the distance of and the magnetic field components at certain x values that we called R20, R70, R120, and so on. For the off-axis magnetic field calculations, calculate the distance when the net magnetic field is at 100 microtesla, then move your phone up and down on the y-axis without tilting it at all and record the different values. I forgot to include this on the last slide, but as you could see before, the system is the magnetometer and the iPhone, and the surroundings is the bar magnet and the Earth. As for the assumptions, there were two major. One is that there is no other external magnetic field affecting the magnetometer, only the magnet. And the second is that the magnetometer of the phone is accurate and not changing with anything that happens during the time you're recording. As for the statements that describe what I observed that when the magnetometer is far from the magnet, it measures a near zero magnetic field in the x direction. And I saw that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. As for the expectations of the experiment, I expected a value of approximately 1 for the magnetic dipole moment, a value of -3 for n, and from the n value, the magnetic field should depend on the distance by a factor of 1 over r cubed. And finally, I expected that as the distance is decreased, the magnetic field should increase. Here's the coding for the experiment. The left side is where the code starts, and you can see the constants, the dipole, the distance, the scale factor, and the different vectors being created. And on the right side of the slide, you can see the application of the vectors to make the arrows that you will see on the upcoming slide. Here's the graphical representation of the coding you saw in the previous slide. The blue are the off-axis arrows, and the orange are the on-axis. And in the bottom left corner, you can see b-axis 1 through 2 values and the b-perp 1 through 4 values. You can see that d is equal to 0.222032, and that b at a 45-degree angle is the purple pinkish arrow in the top left right corner. Here is the graph of the filled out experimental Excel sheet that we were given, along with all of the data used to calculate and create the graph. Here's the analysis slide of all of the data in the experiment. As you can see, the equation given by the graph gives us our values for n and the natural log of k. And using these two values, you can algebraically solve to calculate the value for the magnetic dipole moment of 0.203. As you can see in the bottom right corner. And you can also see the percent error on the calculation of n, as well as the data for the 45-degree axis that will be covered in the next slide. Comparing the 45-degree axis values for error, you can see that there was relatively good accuracy with the values. However, the measured values were a bit higher. This could be due to a number of things, but for the most part, I would assume that it could be incorrect positioning, improper measuring of the magnetic components, or not ensuring that the magnetic field had an exact value of 100 microteslas when you were recording the values. Now for the additional what-if questions. The answers are there would be a change in the x component of the magnetic field since the phone is no longer oriented towards north. As for the effect, the x component could increase or decrease depending on the relative direction of the magnetic field of the magnet and of Earth. And finally, the n value should no longer be -3. As for the second question, two identical magnets stuck together would increase the magnetic field and therefore also increase the magnetic dipole moment. And to get the same magnetic field as with one magnet, the distance values would have to increase to compensate for the increased magnetic field because there is an inverse relationship between magnetic field and R.